Can anybody hear us?
We can hear you. You have to call 911 about that. Yeah.
It's all unmuted. Anyone that is on the phone listening to the presentation, can you please let us know that you can hear us?
Yes, I can hear you.
Thank you. All right. Just a couple of quick announcements. A reminder to everyone that when you have new employees or new students, to please make sure you send Trisha and I the information for those new employees or students so we can onboard them. We've had a lot of people recently letting us know that they are either not affiliated with CredC anymore, or random people that we all of a sudden are finding out that are affiliated with CredC that are, their names and associations are nowhere to be found. It's really, really important that we have their information, and just as important that when people are no longer affiliated that we know that as well. So please let us know as soon as possible so we can get them onboarded if they're new staff, or taken off of everything if they are no longer with CredC. Also, we have reviewed the all hands meeting surveys, and we have implemented some new steps in making the all hands meetings more efficient and more effective based on your feedback. We appreciate everyone's survey suggestions. So please take advantage of the rubric that was sent out and the suggestions that I have given you based on your feedback. We'd really appreciate these meetings to go to serve everyone as beneficially as possible. If you in the future think of anything that you think would be beneficial for the group, please don't hesitate to let us know of any additional suggestions as well. Dilhan or Trisha, do you guys either have?
Just a reminder that we have a CredC seminar on Tuesday at 3 p.m. And if you go to the website or the invite that was sent out today, there's a live streaming link that will be available.
You know we're all in DC then, right?
Then you won't be here.
Okay. So, Linda, just for the Illinois folks, can I please get a list of all the students associated with CredC and their associated faculty for Illinois, please?
Sure. You can get a list of those, I know.
Yeah.
Sure. All right, I'm going to turn everything over to Grace so she can introduce our presenter today. So, Grace, if you want to take it away. Okay, sure.
So it's my great pleasure to introduce Tara Mina. I've been very fortunate to work with Tara, and she's my currently master's student. And then she's wonderful, and then she's very productive for research, and she already published 2 papers. And then we are going to Stanford for the Stanford Annual PNT Symposium next week. And then her work is actually funded by the Department of Homeland Security, but because this is within a similar scope to CredC, so that's why we have her present in this venue as well. Okay.
Cool. Yeah, thanks, Michelle. Hello, everyone, and good afternoon. I'll be presenting my work on GPS spoofing detection via a multi-receiver hybrid communication network for power grid timing verification. The U.S. power grid is continuously monitored by phasor measurement units, or PMUs, which measure voltage and current phasors at critical substations in the power grid network. And these measurements are then used to estimate the state of the power grid in real time. And for this purpose, each measurement is provided a precise timestamp using GPS, thus synchronizing these measurements across the grid network with a common timing reference. However, because civilian GPS signals are weak and unencrypted, they're vulnerable to spoofing attacks. And indeed, a significant timing inaccuracy could induce a generator to trip, as shown in Daniel Shepard's work. And what was it? Switch. Sorry, so significant timing inaccuracies could induce a generator to trip, as shown in Daniel Shepard's work. And as a result, at critical substations, the additional load placed on the neighboring stations could induce these generators to trip and potentially lead to cascading failures and large-scale blackouts similar to the northeastern blackout of 2003. And orthogonal to the civilian signal are the military PY codes, which are encrypted and thus cannot be reproduced by a spoofer. As a result, this quadrature phase signal component establishes a type of signal signature in the background of all authentic GPS signals. And as proposed and demonstrated in the work done by Sherman Lowe as well as Mark Psyche and Todd Humphreys, the presence of this signal can be detected without precise knowledge of the bit sequence by correlating a conditioned signal snippet with multiple receivers. And using the encrypted codes in this way, we've shown in our prior work that a handful of receivers can be authenticated by comparing the GPS signals. Additionally, we've demonstrated that the ability to detect the spoofing attack using a centralized framework architecture. For a small number of receivers, we can utilize a simpler framework with a centralized processing station, which receives signal samples from each receiver, processes it, and then sends back a corresponding spoofing decision. However, for the power grid network, with nearly 2,000 PMUs widely dispersed across the continent, we need a more suitable architecture. So as a result, the key objectives for our research are to utilize the existing power grid resources to develop a multi-receiver spoofing detection architecture to authenticate each PMU within the power grid network. And additionally, we hope to further consider the potential for a coordinated attack against regional collections of receivers within the network. And furthermore, we hope to, we test our algorithm with data collected during a government-sponsored live sky spoofing event, demonstrating that our algorithm can successfully evaluate the authenticity of each receiver during a real-world spoofing attack. So first I'll explain the proposed multi-receiver communication architecture before discussing the details of the algorithm, and then I'll conclude with our experimental results and summarize our work. One standardized communication architecture or communication infrastructure proposed by the North American Synchrophaser Initiative is called NASPnet. And this network structure allows for the communication of PMU data throughout the power grid network. And as shown in this figure, the architecture is made up of several utility subnetworks, each of which is made up of a collection of PMU devices, as well as a central processing station, which is usually a phaser data concentrator or the PDC. Then each of these regional networks is connected in a distributed manner via the NASP data bus. And the data exchange is available between any two nodes within the power grid network. However, most of the available bandwidth and communication resources are prioritized for these individual regional subnetworks. So our proposed hybrid architecture will overlay the NASPnet communication structure. And thus we'll have a large-scale distributed network of central processing servers, which are usually PDCs, each of which branches out in a centralized manner to its regional collection of PMUs. And thus, signal snippets can be initially compared within the regional network, where the communication resources are abundant, and then each regional network can compare a condensed version of its received signals with the other more distant network sites for verification. In this high-level diagram of our algorithm, we focus on the processes performed by a single PDC, or a single centralized station within the hybrid network. In the regional network, each PMU sends raw signal samples for a particular satellite time of transmission, which is determined during its scalar tracking. And in this way, the signal snippets are all pre-aligned according to the time of transmission when received at the PDC. And this significantly helps with peak detection, especially in noisier conditions, as we see in the upcoming slides. And the PMU also sends its signal parameters computed during scalar tracking for each of visible satellites. And from these parameters, the PDC generates a conditioned signal snippet for each received signal. And then it performs pairwise cross-correlation amongst between each pair of snippets within the network. Between each pair of snippets with the common PRN. And then aggregates the results to determine the preliminary spoofing decision for each receiver. And this is based on data in the regional network only. Next, the PDC then compares its received signal with those from other distant sites to verify the preliminary spoofing decision. And this step is particularly valuable in the case of a more sophisticated coordinated attack against the regional network. And to reduce bandwidth and processing requirements for this step, the PDC creates a regionally representative snippet using the signals initially evaluated to be authentic within its regional network. And it sends copies of this to other PDCs through the distributed architecture. And upon receiving data from the distant sites, the PDC then compares these signals with its own representative snippet to determine the final spoofing decision, which is then returned to each PMU within the local network. Now I'll describe the details of the algorithm performed at each PDC. So going more in depth from the high-level structure, after conditioning and performing the pairwise cross correlations for each pair of receivers, the PDC then computes the pairwise statistic based on whether the signal, whether the correlation signal peak is sufficiently large, as well as based on the peak to noise ratio of the cross correlation results. And then these pairwise statistics are aggregated for each PRN, and then again for each receiver to determine the preliminary spoofing decision, or the preliminary spoofing statistic. And if that statistic is above the preliminary threshold, we initially conclude that the receiver signal is authentic. Otherwise, we conclude that it's spoofed. And then from the snippets preliminarily determined to be authentic, the PDC creates a regionally representative snippet. And this is actually created by finally aligning the conditioned authentic receiver snippets to the nearest sample for each PRN, and then performing a weighted average according to the PRN-specific statistical contribution for each of those authentic receivers. So continuing on, when receiving the representative snippets from the distant site, the PC then compares the region representative snippet, or it compares these distant signals with both its own regionally representative snippet as well as the signals preliminarily determined to be spoofed. So for both sets, the PDC performs the pairwise cross correlation, computes the peak to noise ratio, and then aggregates the results to compute the final spoofing statistic.
And what was PRN again?
Oh, sorry, PRN for each of the satellite signals. So for each of the PRN IDs for each of the satellite signals, it does this.
Can you comment on what PRN stands for?
Pseudo-random noise, because each of the satellite signals has a pseudo-random noise code. It appears random, like a random sequence of ones and zeros, but it's actually an identification for that particular satellite, and it allows for code division, multiple access. Since they're all the same frequency, you can just interpret the signal from one satellite using that PRN code.
Is that different from a PNR?
Yes, sorry. PNR is a peak to noise ratio in this case. Yeah, sorry, yeah. Yeah, so then once the final spoofing statistic is computed, then the PDC checks whether the statistic is above the secondary threshold. And again, this is computed for both the signals which were preliminarily determined to be spoofed, as well as the collective signal snippet from the receivers determined to be authentic. And for the initially determined to be authentic receivers, if it's above the preliminary threshold or the secondary threshold, we then confirm the authenticity of these receivers. Otherwise, if it falls below, indicating a poor signal match of this collective snippet with the other distant sites, we determine these receivers to be spoofed in a coordinated manner. Yes?
Do you assume that multiple PMUs are getting, have the same satellite constellation in view so that they're seeing the same PRNs?
Right. We're, because because the regional network is not too close, but it's in general like maybe a statewide network, we assume that they have a lot of similar PRNs.
Okay.
Yeah, it's a good question, yeah. And then similarly, for the receivers determined to be spoofed initially, if the final spoofing statistic is above the threshold, then basically indicating a strong signal match with the distant network, we conclude that these signals are in fact authentic. Otherwise, if it falls below, we confirm the lack of authenticity of the received signals. So now I'll discuss our experimental setup and results. To verify our spoofing detection algorithm, we recorded GPS signals during a live sky spoofing event in a western U.S. state. And simultaneously, we also recorded data at several other sites, including 3 sites in the United States, which was Illinois, here in Champaign, Ohio, and Colorado, as well as 3 sites in South America, which were Peru, Tololo, Chile, and Pachón, Chile. And we used a sampling rate of 2.5 megahertz, which is significantly below the Nyquist rate for the PY codes, but we gain enough of the signal characteristics to compare them and detect a signal match. And at each station, we recorded data with a universal software-defined radio triggered by a chip-scale atomic clock. And then the data was then later post-processed with our research group's object-oriented software-defined receiver written in Python called PyTNSS. And for our experimentation, we used snippet lengths of 500 milliseconds. So here's a plot of the quadruplet phase signal correlation between the Colorado and Ohio site for PRN 22. And this PRN was received at an elevation angle of 71 degrees in Colorado and 51 degrees in Ohio. And this represents a typical cross-correlation plot we observe if both of the received signals are authentic. And as you can see, there is a single large peak significantly above the noise floor, close to zero lag. And this correlation peak is near center without any additional alignment performed by the PDC, since the signal snippets sent by each PMU, each receiver, correspond to a particular time of transmission. Thus, the PMU, which is continuously tracking its received GPS signal, maintains an estimate of this time of transmission and sends the 500 millisecond signal sample which corresponds to that time. So any offset from center of this signal peak occurs due to error during the tracking at the PMU site. So by having PMU send snippets according to its tracked time of transmission, the PDC doesn't have to perform further alignment of the received signals. And additionally, by using knowledge of the tracking accuracy, we can quickly seek the correlation peak within a narrow window from the center, even with much noisier correlation plots, like as we see in this next slide. This is an example of one of the receiver correlation plots we observed between two authentic receivers. Some of the data from our receiver in Tololo, Chile was particularly noisy, and this was reflected in its cross-correlation plot. This receiver, however, maintains lock of the signal continuously during signal tracking. And the largest correlation result throughout the plot is represented by the red star in this plot. However, this corresponds to an error of over 100 milliseconds in tracking. So we can disregard this peak as being due to noise. And the largest peak within our tracking error window corresponds to the yellow star, which is significantly above the noise floor, indicating that this signal peak is likely authentic. But using the time of transmission for pre-alignment, as well as the knowledge of the tracking accuracy, we can still pick out the authentic signal peak in a noisy correlation plot like this one. And similarly, by using the knowledge of the tracking accuracy, we can avoid choosing the wrong peak in some cases if we have noise within the correlation result of the spoof receiver. And here in this plot, you see the cross-correlation between the western U.S. state and Colorado for PRN 22, which was received at an elevation angle of 79 degrees at the western site and 71 degrees at Colorado. And again, this peak, because both receivers maintain track of their signal, whether that signal was authentic or spoofed, they were able to send the corresponding snippet for a particular time of transmission. And using the error, the largest signal peak within the narrow band from the center corresponds to the yellow star, which is barely above the noise floor. As a result, in a case like this one, where the plots have additional noise, and potentially the noise here comes from a residual of the authentic signal peak, since it was such a high elevation satellite that the gain margin was potentially larger compared to that from the transmitter, for the spoof transmitter. But in a plot like this one, we would avoid choosing the red star, which would be deemed sufficiently large enough above the noise floor to be considered authentic, thus potentially resulting in a misdetection for the spoofing attack occurring at this receiver. So examining several minutes of data during the spoofing event, we computed the preliminary statistic for both the U.S. regional network, which contained Colorado, Illinois, and Ohio, as well as the spoofed western U.S. state. And we also computed the preliminary statistic at the South American site, which contained Peru and the 2 Chile sites. So from this plot, you can observe the histogram of the preliminary statistic, as well as that for the authentic data, as well as that for the spoofed data, both of which appear to have a distribution which is similar to a gamma distribution. Fitting these 2 data sets with a generalized gamma distribution function, we defined our preliminary threshold by choosing the intersection point between these 2 probability distributions. Thus, if we computed the preliminary statistic, or if we assume our preliminary statistic computed comes from either the spoofed random distribution or the authentic random distribution, our threshold is chosen to maximize that the conditional probability of our statistic this way. So if our preliminary statistic lies above the threshold, we determine that the receiver is most likely coming from the authentic distribution, whereas if it lies below, then it's most likely coming from the spoofed. And as you can see in this slide, the preliminary statistic, which is computed for each regional network, shows the authentic receivers from Illinois, Colorado, and Ohio, which were all distinctly above the preliminary threshold, which is designated here in the pink dashed line. Whereas the spoofed receiver in that U.S. regional network the preliminary statistic lies consistently below the threshold, thus achieving the preliminary decision of being spoofed. And similarly, computing the statistic within the South American regional network, each of those authentic receivers remain consistently above the threshold. Now, to verify the preliminary spoofing decision, a regionally representative snippet was created for the U.S. network using the signals preliminarily determined to be authentic, the Illinois, Ohio, and Colorado. And then this representative snippet from the U.S., as well as the original snippet from the receiver initially determined to be spoofed, were both compared with the representative snippet from the South American site. And as you can see in this plot, the final statistic for the U.S. representative snippet is consistently above the secondary threshold, indicating a strong match of this collective signal with the South American representative snippet, and confirming the authenticity of these receivers. Similarly, the snippet from the spoofed receiver lies consistently below the secondary threshold, indicating a poor match with a distant region and revalidating the preliminary decision for that receiver being spoofed. In summary, we proposed a hybrid architecture to detect spoofing on PMU devices within the power grid network. And this architecture also provides a defense against coordinated attacks on a regional collection of receivers. And additionally, we utilize regionally representative snippets in this way from the initially authenticated receivers, thereby reducing additional bandwidth and processing requirements. And finally, we demonstrate that our algorithm successfully operates on a wide spread of network, or a widespread network during a governmentally sponsored real-world spoofing attack. And in particular, it detected signal manipulation at the victim receiver while simultaneously authenticating each of the receivers within the hybrid network. We'd like to thank Professor Jade Morton and Mr. Steve Taylor for collecting data at the South American sites, as well as the Colorado and Ohio sites. And additionally, we'd like to thank our lab members for the data collection and the experimental setup at the Illinois and the spoofed sites. Okay.
Chub. Does anyone on the phone have any questions or feedback that they'd like to give Tara?
Can you explain what a snippet is?
Oh, it's like a signal sample that, for our case, we chose a 500 length signal sample.
500 what?
Or, sorry, 500 millisecond length. Yeah. Yeah, it's
So
just
it's a sample of an actual transmission?
Right. We take a 500 millisecond sample of the raw GPS signal that each receiver receives, and then from that we create the conditioned signal samples for each of the PRNs, for each of the satellite signals.
Did you take all of them at the same time?
Right, exactly, and then we correlate for all of the PRNs in common within the network.
So there's no decoding, right? It's a raw amplified receiver voltages. Do I understand it?
Right.
Yeah, but there's kind of a decoding, because I think, there are a lot more details. For example, all the satellites, they are moving, they're orbiting, so they all have different Doppler effects.
Yeah.
So the receive signal, they all have different, slightly shift in the carrier frequency. And then they also have different code offsets, and then they have different phases. So we have to do a lot of signal processing to condition it. In addition, the receive signal is really, really weak. So when we align them, we also have to use certain correlation different signal processing techniques to boost the signal, the correlation piece above the noise floor.
Mm-hmm.
Yeah.
Because the other question I had was on the correlation, you showed that both satellites were pretty high in the sky.
Right.
What happens at lower elevation? Does the phase shift because it's longer, travel through the atmosphere?
Yes, a lower elevation because you have longer, the path through the atmosphere, so you just have more, we call atmosphere delay. So the delay caused mainly by atmosphere, but there's also some delay caused by troposphere. And also if you have lower elevation satellites, just think about all these buildings, right? You have a higher chance of the signals getting reflected or blocked, so you will have more errors. But the nice thing about this algorithm is that because there's a kind of building redundancy from the satellite system, at each side we will have around the 10 satellite view, some are high elevation, some are low elevation. As long as we have one, the sites have one satellite in common, you can use this military code signature for the cross-correlation comparison, right? And then given that we have multiple, so we have that built-in redundancy, and because we have that redundancy, we can typically select a subset of the high-quality satellites to compare, or we can also, by design, choose to give different weights to different satellites of different applications.
So there's really no reason why you couldn't also extend this off to the Russian satellites or Chinese satellites?
That's right, it's the same technique. Yeah, it's just, for now, we only did it for the US, mainly because, for this type of work, it's really hard to do real-world experiments because it is illegal to jam or to spoof. And then, so we are very lucky that this is a very prestigious event, because this is a really important domain. So there's a government-sponsored live jamming and spoofing event. We're not allowed to say the word, but it's in the middle of nowhere in the Western state. We're allowed to say it in the Western state. So we actually traveled up there, and then it was really tiring because it's a whole week, and then every night from midnight to 5 a.m.
Right.
Because we want to have a minimum disruption to normal people.
Sure.
Yeah.
That's why I was wondering why you guys were saying Western United States without actually pinpointing a location. So this one is really, really remote area, and then we actually participate in another jamming event, which is not so remote. And then in order to do that, actually, they have to notify all the police officers because when they drive police cars at night, their GPS won't work. And there are a local mining company nearby, all the mining companies, they use precise GPS for driving their mining machine. And they have to tell them, because the mining machine normally operates 24/7, tell them, don't do that for this week at night because it won't work. Or even the spoofing event, they make a drive to a different place, right? And then they also have to work with the air traffic. If there are any airplanes flying by, they have to reroute the air traffic.
So it's really a lot of work to have such event, and then we are very, very lucky. Even like, I think they only select a very small number of groups to be able to participate in that. And then we got selected. And then we collect that data, and also like we simultaneously were collecting data at all those sites, almost like in Chile, Peru, other parts of the U.S. So it's a lot of work. You know, my students here, they also have to do that in the middle bank. We have to collect the data at the same time.
So I think that picture of the three of you with the car door open with all the equipment on the seat, that should be on some university site.
Yeah, that's actually like before the test, because all the testing is during the night, so it's dark, right?
Yeah.
So we have to go there like kind of before dark and set everything up.
Yeah, I guess if somebody says, oh, I know where that cactus is.
And then just speaking of that, just some relevant information you might be interested to see, that just for this week, and then there's news that there's a company in Hong Kong, they actually fly drones, and they can like make a nice picture in the sky. So they were flying a bunch of drones, and then to like show some birthday something like in the sky, and then someone needed the GPS jamming, and then 46 of these drones crashed, and then the company lost over $1 million.
Wow.
This is just this week.
Did they catch the person or?
Not yet.
No, okay. So,
But,
oh, sorry.
yeah, but the rest is just like they crash all the room, just for this.
So, you said it's illegal. Is it only illegal in the US or is it illegal everywhere? They just broke the law?
No, it's illegal. Different countries have different laws.
Gotcha.
Some of my colleagues go to some other remote countries to do some experiments. In those countries, it's a gray area.
Okay.
It's not legal, but
It's not illegal as well?
it's not clearly illegal. But we are very nice people, right? We never try to go to that gray area. So, but because our research luckily got a lot of government attention, and then our group is pretty well funded by the government agencies, so we got invited to this legit legal exercise.
The Python GNSS, you said it's a software-defined what?
A receiver.
Receiver. Would that be usable as a transferable technology, maybe?
Oh, yeah, maybe. It's just basically it takes in the raw. We're actually working on a real-time receiver as well, where it would take in the raw signal in real time and then process it in real time to give you your navigation solution.
This is really good stuff, but there are maybe multiple components that could be of interest to the transferable with some kind of an open source or form or something like that.
Right. Yeah. No. Exactly.
Gotta have that mindset.
Nice.
Yep.
Anybody else have any content questions or feedback? Okay, before we dismiss, I do want to say a couple of things. Just because these meetings are also to help with practice on presentation and communication. And I want to applaud you. I think your slides were done very well. I really appreciate how you weren't reading your slides to us, how you used your slides to support what you were saying, especially with slide 6. And the content of your material is difficult for me to understand as this is not my background, but I actually understood some of what you were talking about, which is important for everyone to remember that some of the industry people that you guys come in contact with aren't always going to be educated in exactly what you're talking about. So it's going to be important that you utilize language that demonstrates your education and your ability to discuss your topics well, but is also easily understood by others who don't have that same background, and I think you did that very well. Those of you who are online obviously can't see her, but she did a great job with eye contact. Your body language was very relaxed, which was great. You did a great job answering questions as they came up. Your slides were clear. I also made notes of the questions that were asked, so I will send those to you in case those are things that you want to include in your slides, maybe at a later date, if you find that that's information that you should include. The only suggestion that I would make, and this is something for other people to keep in mind, anytime that you're presenting information, out of politeness, we tend to apologize. And so when you were asked a question, you were like, oh, I'm sorry. Try to avoid apologizing because you didn't do anything wrong. And it kind of takes away from you and what you're saying. And you only did it to be polite, but you were answering his question as he presented it. So that's the only suggestion I would make is in the future to avoid that as a presentation, because you want to make sure you seem sure of yourself and what you're presenting. But overall, I think you did a fantastic job. So I'm going to try and do a lot more of that kind of feedback since that's my background, and I think that that will be helpful for everyone involved, specifically the students that are presenting. It's really important that you guys get that feedback, especially when you're going to conferences and other types of events where you're going to be in front of a large audience that you are expected to interact with. So, great job.
Yeah, thank you so much. It was really useful feedback.
Does anybody else have anything? No? All right. Thank you, everybody. Have a great afternoon.
Very nice. Good job. Oh, thank you. That was like a feedback. I see you. Oh, wait a minute.